Suppose you have three features in your dataset: temperature, lab test, and sore throat. Your response variable or your target variable is strep throat. So you are given a bunch of data points. These green data points represent not strep throat, that means negative class, and the red data points represent data from strep throat class. For a new data point, for example, this one, our job will be to classify it correctly as either green or red. So the nearest neighbor algorithm, what does it do? For unseen data points, it calculates the distance with the existing data points. We have these green and red existing data points. And when we will be given this new case, it has some value for temperature, sore throat, and lab test. Using those values, this is suppose its location in this space. Now, it will look at all the data points and calculate the distances and pick the one with the lowest distance. In this case, this green one. And the nearest neighbor algorithm, it assigns the same class as the nearest neighbor to the unseen data point. As the nearest neighbor is green here, the prediction on this unseen case will also be green. Now, you can take one nearest neighbor or multiple nearest neighbors. For example, you can take three nearest neighbors. Suppose if you take three nearest neighbors, these are your neighbors that you will consider for assigning the class of this data point. In this case, all these are green. So it will assign the class of this unseen data point as green. If all of them are not from the same class, we will assign the class of the majority. For example, here, if we take more neighbors, suppose we include this one, we include this one as well, and we include this one and this one. In this case, we have 1, 2, 3, 4, 5. 5 green data points and 2 red data points. It is 5 versus 2. Majority of the neighbors are green. So we will assign green to this unseen data point. Nearest neighbor algorithm is one form of case-based reasoning. Now the question is, how can we measure similarity or distance? For continuous variables, we can take the Euclidean distance, or we can take Manhattan distance. For example, A and B are two data points here. If you take the green line, that is the Euclidean distance between A and B. You can also take the Manhattan distance, where you can only move horizontally or vertically. So in that case, the red or the blue or the yellow, they will represent the Manhattan distance. You can also take correlation as a metric. For example, in this case, we have plotted days and the temperature. A is a vector or an array of data points. Suppose you have 4 data points for A. You have 4 data points for B and 4 data points for C. And those are numeric data points or continuous variable. In this case, if you take Euclidean distance, then B and C are the closest pair here, right? Among these three, A, B, and C. But if you take correlation, that means if you look at the changes, A and B change in a similar way. In that case, A and B will be the closest pair if you take correlation. Consider this following example. You are given speeds of different autonomous vehicles at different time points. Suppose you have car 1, you are given a bunch of speeds, okay? For car 2, you are given a bunch of speeds. And for car 3, you are given a bunch of speeds. Now your job will be to classify what is the manufacturer for each of those cars. Now, if you know that cars from the same manufacturer accelerate the same way, in that case, instead of looking at the speeds, you would look at the change in speeds. So even though at different time points the speeds are similar, you may not consider them as the nearest neighbors. Rather, you would look at the acceleration, and based on that, you would classify the manufacturer of those autonomous vehicles, whether it is Waymo or Tesla or Cruise or whatever. For discrete variables, we can take overlap coefficient or Jaccard index. The Jaccard index can also be called as intersection over union. You can take, in this case, suppose you have two patients, A and B. Patient A has fever and inflamed throat. Patient B has fever, they don't have inflamed throat, but they have a positive lab test result. In this case, if you take the Jaccard index, one way can be just counting the number of common features and counting the number of uncommon features. The number of common features is 1, just fever is common. Number of uncommon feature is 3, I, not I and L. And if you take intersection over union, then union means basically common plus uncommon. So union is 4. There are 4 different feature values: fever, inflammation, not inflammation, and positive lab test result. So in that case, 1/4 would be your similarity metric. So Euclidean distance, Manhattan distance, those are measures of distances. In those cases, the nearest neighbor will be the one with the lowest value. On the other hand, correlation coefficient, Jaccard index, they are measures of similarity. In those cases, the nearest neighbor will be the one with the highest value. Now let's see, how does the value of K affect your classification? So in this case, K means how many neighbors we are going to look at, or how many neighbors we are going to consider. In this example, suppose the data points have 2 features. Feature 1 is plotted along this axis, and these are feature 2. Okay. Now, the blue data points, they belong to one class, and the red data points, they belong to another class. Our objective is to classify this green data point. If you pick K equals to 1, in that case, the nearest neighbor will be this red data point. So the classification of this green data point will be red. If we choose K equals to 3, we will have 3 nearest neighbors, this red one and these 2 blue ones. In this case, majority of the neighbors are blue. It's 2 versus 1. So the classification will be blue. Again, if you take 5 nearest neighbors, K equals to 5, then these 2 neighbors will also be included. It will be 4 versus 1. The classification will be blue. If you take 11 nearest neighbors, in that case, these blue points and these red points will also be included. So we will have 1, 2, 3, 4, 5, 6, 7 blue points, and 1, 2, 3, 4, 4 red points. That means the majority is blue, so blue will win. How can we choose an appropriate K for a study? If K is too small, it can be sensitive to noises. And if K is too large, it may have low precision. So what does it mean? Consider this example. In x-axis, we have number of cigarettes smoked in last 5 years, and in y-axis, we have the age of a patient. These green ones represent healthy people who don't have lung cancer, and these red ones represent people with lung cancer. Now we're talking about the problem with a low value of K. If K equals to 1, suppose we have a new data point here. We don't know the class of this data point. If we choose k equals to 1 and this green one is its nearest neighbor, what will it do? So it will say, okay, the nearest neighbor is green. It's a healthy person. I don't have lung cancer. But in this case, this green data point, it's an anomaly. It's not a regular data point. When we have a bunch of data points in real data, there will be some anomalies. And if the value of k is very low, it's more likely that it can pick up, the nearest neighbor algorithm can pick up an anomaly as the nearest neighbor. So the classification will not be right. How do you solve it? If you take k equals to 3, suppose, in that case, these two will also be considered, and the majority will be red. So the classification will also be red, which makes more sense because this new data point is in the neighborhood of people with lung cancer. Now, what happens if you consider all the data points as your neighbor? So in that case, we would have 1, 2, 3, 4, 5, 6 red data points and 1, 2, 3, 4, 5, 6, 7, 8, 9 green data points as a neighbor. So you are taking k equals to 15. In that case, even though you are in the neighborhood of red data points, you may consider yourself green because you are taking too many neighbors that your radius has stretched beyond the neighborhood of the red data points. You are just taking all the data points as your neighbor. So if k is very low, it may be sensitive to noise. That means it may choose an anomaly as the neighbor. And if the k is too high, it will have low precision. So in that case, it will just look at so many data points that the significance of the distance metric will lose its value. How can we choose a good value for k? One way will be to look at different values, then making predictions and looking at the performance, suppose accuracy. In this case, suppose you are choosing k equals to 1, 2, up to 12, then you are plotting the accuracy. Then you see that k equals to 9 is giving you the best accuracy. So you will choose k equals to 9. One important thing here is that this accuracy has to be measured on unseen data. You cannot do it on the data that you have already seen. Ideally, in these cases where we have to tune some hyperparameter, for example, in this case, the value of k, we use part of the whole data set that is called validation data set. Suppose you have a bunch of data points here, red, blue, green. Now, how do we draw the decision boundary? You can consider decision boundary as some sort of wall that separates data of one class from other classes. For drawing decision boundaries in nearest neighbor algorithms, there is a process. So let's see this example here. We have data points from red, green, and blue. So the decision boundary is drawn in an iterative way. We'll have to choose the closest pair of opposite classes. In this case, suppose this red and green. We will imagine a hypothetical straight line and we will draw a bisector. This bisector now separates the data into two groups. The next step is to check if there are mixed data points in one side of decision boundary. For example, in this case, we have green and also blue on this side. If we have such cases, in that case, we will have to draw another line. Suppose this is the closest pair now. Consider a hypothetical straight line and then draw a perpendicular bisector. Now we will combine these two straight lines. And if we combine, it will look like this. Now we have three groups. On one side, we have the green data points. On one side, we have one red point. But on this side, we still have mixed data points, red and blue. Take closest pair of opposite classes again. draw a bisector, then combine the lines. Now it will look like this. There's still a problem. There's one data point on the boundary. So technically it creates an ambiguity on which class does it belong to. Let's take closest pair of opposite classes again. In that case, it will be this pair. Then draw a bisector. Now combine the boundaries. Finally, the decision boundary will look like this. Now we have all the data separated in their own groups. We don't have any group with mixed data points. So we can stop drawing our decision boundary. So this is the algorithm. While we have points in different classes in the same group, find the nearest pair involving 2 points in different classes. Initially, we chose this pair. Then draw a line L1. This is our L1 line connecting the pair. Then draw a line L2 perpendicular to L1. This bisector is L2. So we will draw these kind of lines, and finally connecting L2 lines will give the decision boundary. So that's how you will have to draw the decision boundary in your homework. If you still need any help, feel free to reach out anytime.